Hi and welcome to this chemistry lesson. In it I want to look at the topics activated complex and activation energy. But in order to really understand it fully, we do need to briefly look at a different topic that really doesn't form part of this course, but is helpful to understand. And that is called reaction mechanisms. A reaction mechanism. Now, a reaction mechanism refers to how a reaction actually occurs, and I think the easiest way to explain it is just by using a very simple mechanism. So what we have here is we have a propene, okay, that is hydrocarbon with a double bond between the first and the second carbon, and then we also have it interacting with hydrochloric acid, and you might recall that this is called a hydrohalogenation of an alkene. In other words, we add a hydrogen and a halogen, hydrohalogenation, to an unsaturated hydrocarbon. In this case, we have propene, and that produces this. But how does this reaction actually happen? How is it that this actually happens? Now, what we have here is important. Is we have hydrogen and chlorine, and let me change that one to a pink. Okay, we have hydrogen sharing one of his electrons with chlorine, but now chlorine is highly electron negative. You will recall electronegativity refers to its desire to get electrons. Now chlorine is highly electronegative compared to hydrogen, which is average in a sense, okay, electronegative. But chlorine would very much want to take this extra electron. Actually, that is not right. Okay, he would very much like to take this electron. He's got 1, 2, 3, 4, 5, 6, 7 of his own, and then he's sharing one with hydrogen. But if he could have its way, he would really take that one from the hydrogen. Okay, now hydrogen would give it away if he can get one elsewhere. Okay, so where is it likely then that he could get another one? Well, carbon has more or less the same electronegativity than hydrogen. They're not far apart in their desire for electrons. But if I look at this carbon chain, you will notice that this carbon is connected to 2 other hydrogens and 1 carbon itself. So this carbon, the first carbon, is sharing his electrons with 2 hydrogens, and 2 of his electrons he's sharing with another carbon. Okay, so and this carbon is sharing his electrons with 3 carbons. 2 of them are shared with the first one and 1 with that carbon. Okay, and this hydrogen, and he's sharing 1 with the hydrogen. Now, for reasons I don't want to really get into now, it is this second carbon here, in the carbon with the double bond that has the fewest hydrogens, that is most likely to donate his electron to the hydrogen. Okay, so if that happens, we have, and let's do that in a different color, as we've got this electron here and this electron there. Okay, this blue electron is the most likely one to get donated. But how will that happen? Well, it can only happen if there is a collision between these 2 molecules. If that collision happens in exactly the right way, or in the ideal conditions, then this carbon is attracting, of all of these elements that are attracting their electrons, that blue electron is the less attractive. Okay, if that makes sense, to this carbon. Okay, he's the most likely to divorce his blue electron there, and if that happens, so if there's this hydrogen this chlorine very much wants this electron, so hydrogen is willing to give it away, but he needs an electron somewhere else, and the best place to get it is from this second carbon in the propane. So just before before this exchange happens, hydrogen needs to give away his electron, leaving him now with an excess of protons. Only one, but it's more than the no electrons he has. Okay, chlorine is very happy with all 8 of his valence electron spaces are now filled, but that leaves him with an excess of electrons because he has more electrons than protons. So he now has a negative charge, and in this or what happened here is that it needs to happen that this ion here collides at the right time with this part of the molecule, and because he now has a greater desire for an electron than this specific carbon, remember this carbon doesn't have his normal electronegativity anymore because he's in bonds with other elements. Okay, so some of his valence electrons are already satisfied, so he doesn't hog that one with as much intensity as when he still only had 4. So what happens when this ion bounces into that molecule in exactly the right way, then this blue electron gets divorced from his carbon and now joins the hydrogen. But before that happens, again, the carbon needs to donate it. Okay, so this carbon like that, okay, H2, this carbon now only has a single bond with the second carbon, which has a single bond there, and the second carbon now has a positive charge. Okay, the second carbon has a positive charge because this carbon is missing an electron. This carbon here has a negative charge. Okay, and because of that, this definitely happens. Okay, the right collision between these two happens, and so this becomes CH3. The second one is still CH with a positive charge, and then CH3. So this is all happening obviously in so quickly that we can hardly put a time limit or a time frame to it. But now what happens is we've got this positive charge on the second carbon and negative chlorines hanging around, so the likelihood of them interacting is very, very high. So if there's again a successful collision between this chlorine who doesn't have the same electronegativity as before because he's got extra electrons, this one has a higher electronegativity because he's lost electrons now. Okay, he wants electrons back because he's given away his electrons. So the likelihood of these two now interacting and then sharing this additional electron that chlorine got from hydrogen is very high. And then what we would have is our carbon CH3, and here we would have our CH, but the chlorine will now also share his extra electron to form a bond, and then CH3. Okay, and now we can see this is where we have our chloro, 2-chloro propane. Okay, but in order to have gotten here, we had this whole intermediate process. Okay, we've had all this intermediate processes. So between our reactants and our products, we had a bunch of intermediate products before we got to our private we had a bunch of intermediate products before we got to our final product. Okay, so we've been looking at chemical energy and potential energy that exists between in a molecule. So we have a total potential energy for this. Okay, so this is let's call this my UR1. That would be my potential energy that exists here, and that is my UR2, and R representing the reactance, and then this one is my UP1. Okay, now in these cases we now have a bunch of intermediate products, and let's call them UI1 and UI2 and UI3 and then UI4. There's a bunch of ions that are created in between that also have potential energy in themselves. And as a matter of fact, because they are so highly reactive, they have such a high possibility of reacting with other elements because they have charges in themselves. They are very reactive. Okay, it means that their potential energy are much higher than, well, not much higher, but definitely higher than the original states of the compounds itself. Okay, so if we were to add up these two, that would give me my my total potential energy when I start. So if I were to draw a graph, okay, and on here I've got my potential energy, okay, U, got my potential energy, and on here I've got time. So in the beginning of our reaction, if we add up the potential energy, we might get something that's here, okay? And then afterwards, if we look at our product's potential energy, we've got this one product, and I have it on good authority that it is lower, okay? So in the end, I will have a lower potential energy than I had in the beginning. And in the previous lesson we learned that if my reactants had a higher potential energy in themselves and my products have a lower potential energy, then we looked at the heat of a reaction. That is the potential energy of my products minus the potential energy of my reactants, and in this case we see if this is smaller than that, this will be a negative, less than 0, which means it is an exothermic. In other words, it releases heat. So not just is this the product, there's also another product called heat. Okay, but now in between there's a bunch of other potential energies also at play here, which means between these two, between the initial and the final state, there's potential energies in the intermediate molecules and compounds, which will definitely and always be higher than the initial potential energy, and it will always be higher than the final potential energy. So let's say it peaks there. Whatever that is, it peaks there. Now, what will this graph look like? Because it's not these dots. It is a smooth graph, and it will look like this. Okay, before there's a successful collision, and then there's a successful collisions happening, and at some point I reach a maximum potential energy, and then I start having these intermediate molecules start reacting with one another to produce products, and then the total potential energy goes down and down until I reach my final state, and my reaction products, or my products, are formed more and more, and I've got fewer and fewer of these intermediate states, and this is my final product. Okay, now I've said a lot without actually getting to the topic, but I think up to this point you do have a good understanding of what I'm talking about. Okay, potential energies in the beginning, potential energies in this intermediate phase, and then potential energies of my final product. Now, this is called an energy diagram. An energy diagram, and from this I'm going to take probably less than a minute to explain the words activated complex and activation energy. Activated complex is this point here. The activated complex complex is the highest energy state of the intermediate chemical structure. Okay. That's simple enough. It's the highest potential energies that exist, total potential energies that exist during this intermediate structure that we hardly ever look at, okay, in this course at least. And then the activation energy is this distance. That distance is called the activation energy. The activation energy. So the activation energy is the difference between the activated complex and the initial internal energies. Okay, now this activation energy is the energy that I need to add, or that needs to be added into the system in order for this reaction to occur. Okay, I need to add energy because the energy that I need to add is the energy that breaks the bonds. Remember, we said that hydrochloric acid needs to have a successful collision with that carbon in the middle so that the hydrogen can get it. Now, how do we cause collisions? Well, we add energy. That causes the molecules to bump around more. They get more kinetic energy, and therefore if we add energy into a system, the likelihood of that molecule having enough energy to have a successful collision is more. So this is the energy. Activation energy is the energy that needs to be added to a system in order for that reaction to occur. As soon as it occurs, the rest of the process is automatic, and the rest happens. And then in the end, okay, we have this difference right here. That's the difference between the initial and the final, and we said that is the heat of a reaction, or the enthalpy. And so here I've drawn for us an example of an energy diagram for a exothermic reaction. That just means my initial and my is greater than my final potential energies. If I can draw you a quick example of a endothermic reaction. Remember, endothermic would have my initial potential energy, okay, and my final potential energy would be higher. So again, but here's my final potential energy, okay, but remember the activated complex is always higher than either one of the two. Okay, so I will go up to read my activated complex, and then my final. Okay, there we go. Now you will notice here, okay, that in this case I have a higher activation energy. Now that means that for a endothermic reaction, notice in this case, okay, that the difference between my activated complex and my final potential energies are much higher than in this case. Okay, here that is the difference. Okay, and so the difference between the activated complex and my final potential energy in this case is higher than the difference between my initial energies and my activated complex, which means that heat is a reactant in this equation, a reactant. I need to add heat into this equation. I can always add heat to have enough energy so that I can overcome my activation energy, but then the heat produced, that's the heat produced, this is the heat added, okay, because here I'm going up, okay, here I'm coming down, so here heat is being released. So whatever heat I added at this point gets released again at this point, and after, when it reaches this point, the heat added and the heat released cancels each other out, and now the heat released continues the rest of the reaction. I don't need to continue adding heat. While in this case, the heat that I'm added, when it gets released, okay, there's still this deficit. I still need to continue adding this heat for this reaction to continue to occur. Okay, so I need to constantly add heat, and therefore heat is a reactant. While in this case, heat is just an activation, might just be an activation. There might be different ways of adding this activation energy. Okay, the final thing I just want to say, and I'm sorry that makes this video quite long, but the final thing I want to say is what effect will a catalyst have, and we'll look more at that in a later video. But what a catalyst does is the intermediate compounds that form have a lower potential energy. So I don't know what catalyst we can use in this case off my head just now, but whatever catalyst we use, the intermediate molecule, let's call it the IM, will have a lower potential energy than these intermediate molecules. Okay, what that means is that my activated complex won't be as high. So in other words, it will still look the same, but my activated complex won't look as high as that. So this is with a catalyst. And what that means is that the energy I need to add into the system is less. I need to add less energy into the system to start it going. Okay, but that's basically it. I hope you enjoyed this video and that you learned something. Well, I hope you learned a lot, because I said a lot. I'll see you in the next video. Thank you.